Excellent. Well, that's why we're here today, because I like to use it beyond just my home and beyond where I have typical cellular range. And I'm a professional network engineer. And internet access, once we get away from cities, can be really a big challenge. Sometimes we have great service. I've been to Zion and I've had 5 bars on my cell phone and can barely load a web page after a minute and a half, right? Or I've been out on my Starlink and have, you know, what I think isn't that many trees, but I get dropouts every couple minutes. So I'm here today to talk to you about these concepts. My name's Lyle Tanner. I've been instructing here for 4 years. This is my 4th year. I've been attending for 12 years. I've been overlanding all that time, but I am a professional network engineer. I'm also a radio operator. I teach our GMRS class that's immediately after this class in classroom 2. So that's all about two-way radio communications with GMRS. I also get to go to disaster zones, and so like last year during the Maui fires, I was deployed there for 2 weeks and restoring communications infrastructure. Lots of deploying of Starlink nodes, lots of deploying of the company I work for's wireless connectivity, and I'm very passionate about this. I've contributed to a book on technology, and I just love technology and I love overlanding, and so I'm so excited to be here bringing these two together. We only have 50 minutes, so we're going to go through here kind of fast. What we're going to talk about today, we're going to talk about different types of applications we might use on the internet and why trying to use those while we're overlanding may be challenging and what we can do about it. We're going to talk about the different types of off-grid internet access that might be available to us, what the differences are between them and how we might be able to use one versus another. Really important, we're going to talk about the real basics of the physics of radio frequency. When we're using internet remotely, it is all happening over radio frequency of some kind or another. We're going to talk about some of the equipment that you might be able to use, some of the equipment that I use, and then most importantly, from my perspective, the absolute game changer, how do we take more than one connection, turn it into one virtual connection, so that we're able to get a higher throughput, higher reliability. Quick story, I was driving up here. I had really spotty cell phone service, but I did have service on T-Mobile. I had some service on AT&T, and it would switch between the two, and then I had my Starlink running while driving. I had a really important customer meeting while I was driving, but I took all 3 of those connections, combined them into one, and then the setup was sending the traffic on all 3 at the same time, and then vice versa. On the other side, the traffic was being sent on all 3 at the same time. First one to arrive is the one that gets kept, the other ones get discarded. Using a lot more bandwidth, but it was highly reliable. I had 0 dropouts, driving 70 miles an hour on the highway, going through underpasses, going through trees, and that's what we're here to talk about today. All right, any questions before we get going? Anybody not supposed to be in this class that doesn't want to be? All right, good.
Just keep talking loud.
Yeah, I know, it's really noisy here, which is a great, actually, as we're getting into our, as we get into the RF basics, it's a great example of signal to noise ratio, right? I wouldn't normally have to talk this loud if people out here weren't that loud. So my signal has had to increase because of the noise floor. This is a concept we run into in national parks when we have 30,000 cell phones all trying to compete at the same time and raising that noise floor and reducing the amount of bandwidth that we've got available. So let's move on. So when we try to get to something on the internet, we have a very bi-directional conversation that happens back and forth. It's very chatty. So you'll have, your device will say, hey, I want to get to Google. And then there's something called a DNS service says, great, well, here's the IP address for Google. And you say, great, thank you. And then you say, okay, Google, can you send me some information? And Google says, okay, here's a little bit. Did you get it? You say, yes, I got it. Send me some more. Google says, okay, here's some more information. Did you get it? You say, this goes back and forth and back and forth. This is why latency is really important. Latency is how long it takes for us to send or receive a message, right? And so I've got 2 examples here. We've got latency of 1 millisecond, and we've got latency of 50 milliseconds, right? 50 milliseconds isn't a very long time. Doesn't seem like a very long time, right? 50 milliseconds is pretty darn quick. But with that difference in latency, a TCP transaction just to load that page goes from about 1/10 of a second to 7.5 seconds. So that latency is really important, and we're gonna walk through like how latency gets into the system and why that matters and things that we can do about it. So I already went through a little bit of this in an interaction, but let's do this real time. So I see Roland here. Roland, if I say, here's some data, and then I want you to reply, great, can I have some more? Roland, here's some data. Yeah, here you go. Here you go. All right, now let's put a 10-second pause in that. Roland, here's number 1. And now I have to wait 10 seconds. Roland, here's number 2. Obviously you can see, so when we're talking about satellite internet service providers, there are a couple different types out there. There are those that are geostationary. Those have a roughly 800 to 1,000 millisecond round trip. Or on low Earth orbit satellites, they have a 25 to 40 millisecond round trip. So 25 to 40 versus 800 to 1,000. Obviously, our transactions are going to be highly impacted there. It can be kind of difficult to understand this chart looking at it in this audience with the screen, but I have 2 different depictions of the same thing. So on the right-hand side of the screen here, I've got a chart that maps what our throughput is in megabits per second. So I've got 1 gigabit per second over here. Then I've got what's our round trip time, and we start at 10 milliseconds, and we go all the way to 600 milliseconds. And then the third dimension that I have here is packet loss. Anybody guess what packet loss might be? Yeah, I sent something and it didn't get there, or something was sent to me and it didn't get there. So at 0.1 packet loss, 10 milliseconds, that's our baseline for this diagram, we've got a gigabit of throughput. If my packet loss, only my packet loss changes to 1%, my throughput now is 400 megabits per second. 1% packet loss effectively cuts my bandwidth in half, okay? Same thing on the latency. On the latency, if I go from 10 milliseconds to 100 milliseconds, and I keep my loss exactly the same, if I was at 0.1 packet loss, I had a gigabit connection, and now only thing I changed is from 10 milliseconds to 100 milliseconds, my throughput just went to 100 megabits per second. So now when I start combining these variables, we started off with a 1 gig connection. Now maybe I've got 2% packet loss and 200 milliseconds. We're talking a couple megabits per second of throughput. This is why this stuff is really important, and why learning how to mitigate these things are really important as well. So I'm a digital nomad. I get to work remote sometimes. Sometimes I like to watch Netflix. Sometimes I need to make a phone call while I have no cell phone signal. Sometimes I'll send an email. Probably all use cases everyone in here is familiar with. Just a quick glance at what does that look like. So, uploading multimedia files, that's probably the hardest thing I do as a digital nomad, as an overlander. I'll grab a video from one of my cameras and it's gonna be a couple gig, and I'm trying to do an upload, and it's really difficult because it's very high bandwidth requirement, somewhat sensitive to latency, and somewhat sensitive to packet loss. On my video conferencing though, I have to join WebEx meetings, I have to join Zoom meetings, I have to join Microsoft Teams meetings. Anybody else in here have to join a bunch of them right? Nobody can ever just pick one platform. We always got to have all the different ones. Our bandwidth requirement actually isn't that high. My next chart I'll go into what those bandwidth requirements are, but my sensitivity to latency and loss are huge. Very important that we overcome latency and loss when we're having video conferences. At 80 milliseconds, it starts to feel awkward to have an interactive conversation, right? And there's something called a mean opinion score, or a MOS score. This is used in IP telephony. The MOS score starts to drop off a cliff after 80 milliseconds because you don't feel like you're having a normal interactive. Who here's been on a conference call before and you try to talk and the other person talks at the same time and you're both like, I don't know how long to wait, right? So latency has a big part to play in that, and it really messes with our communication flow.
If you don't use the video part on the camera, does that help?
It can help, depending on whether or not you are bandwidth constrained.
Okay.
So if you don't have enough bandwidth, then you're going to be sharing bandwidth. All of the major video conferencing platforms now are dynamic, and they'll back off the video when the voice is constrained. And so 2-3 years ago, that wasn't the case. But today, if you're on a modern MS Teams, Zoom, or Cisco WebEx, they're all going to dynamically back off that video appropriately to prioritize the voice. but it's our connection. It's our actual connection to the internet that's driving that latency, that 80 milliseconds or above, where it becomes a consideration. VoIP calling, super low on the bandwidth, super low. I mean, we're talking kilobits per second. I can do a voice call in like 64 kilobits per second. Like, no problem to do a voice over IP call. All of your modern smartphones now support voice over IP. So if you don't have your carrier, you connect to Wi-Fi, it's got an internet connection, you can make a call over that if you're on a modern smartphone.
Why is streaming so insensitive to latency effects?
That's a fantastic question. Streaming is insensitive because it's not interactive. And so you have a cache, and so what ends up happening is your, let's say Netflix. You've got the Netflix app on your tablet, your iPad, your Android tablet. It says, I'm going to stream the show, send me the next 10, 20, 50 seconds of data, it stems in, and then it's like, oh, we're starting to get to that section, send me some more, and it'll take it in as fast as it goes, and it'll say, oh, I didn't get half of that, retry it again, and it's really good at recovering from that, but a great question. And then similar with email, pretty low, because it's effectively asynchronous communications. We send a bunch, if it didn't go through, it retries, and we don't even notice. It got put in our outbox, and then it eventually ends up going through. Great questions, by the way. All right, so I have the top 4 video conferencing platforms that exist today. We've got Cisco WebEx, Microsoft Teams, Zoom, and Google Meet. And I just wanted to highlight some of the differences in these products because there are differences in them and how well they work. And I've experienced these differences in real life as well. So on our bandwidth, you can see that for an HD call, all of the bandwidths are 4 megabits per second or under. So if I have a 4 megabit connection, I can do an HD video call, and it will automatically downgrade the video to as low as like 160p as needed, depending on the call. But you can see we can do anywhere from 1.7 up to 4 megabits per second, and that's on both on the upload and on the download side. Now, the latency, we've got a little bit different variances in what latency they'll accept, but most importantly, look at this last column here, loss. So pretty big difference in some of these. A difference on the top one there, Cisco WebEx, and full disclosure, I am a Cisco employee, but you use whatever you need to use. What's happening here is forward error correction. So built into the stream on WebEx, it's doing something called forward error correction, where we're adding additional information to the stream. Think of it like a checksum, so that if we miss a packet, we can use a processor to recalculate what the contents of that packet were based upon the other packets that have come in there. And you'll see that on the other platforms where we can suffer various amounts of loss within the application alone. So that's just if I was doing the application, I was on my cell phone, connected to the cell tower here. If I was trying to have an MS Teams call and I was running into some problems, I might not have that same problem on another platform. But we can actually use some technology on our laptops or on our cell phones to overcome some of this as well. And we're going to be talking about that here in a little bit. I'm going the wrong way. All right, so I mentioned that everything that we do off-grid is always going to be connected via radio frequency, RF. Cell phone signal, that's RF, that's radio frequency. Satellite signal, that's RF. Wi-Fi, that's RF. So it's important for us to understand some of the concepts here of how that connectivity is getting to us and what matters with that connectivity. So because it's an RF signal, all of the frequencies that we use for modern internet communications are considered line of sight. If I can see it, I can talk to it. That doesn't mean if I can't see it, I can't talk to it, but things start to get complicated then. So what this ends up meaning is that if there's a cell phone tower here on site at Fort Tuthill, but I don't have direct line of sight to it from here, which means my signal is likely bouncing around a little bit before it gets there. And I'm not getting as much of my signal to that tower, still enough to get that signal above that noise floor, right? We talked about the noise and the signal. But one of the things that I can do in all of this is always improving my line of sight. So on my cell phones, that's typically, I can stand on top of something, right? I can get up to higher ground. On my Starlink, it could be I get out of the foliage. I get a broader view of the sky in order to get a better line of sight to that. On the mobile networks, practically speaking, we're typically seeing not typically more than about a gigabit per second unless you happen to be in a highly dense city and we're using something in like the 40 gigahertz range. But we're not going to find that while we're overlanding. So typically we're going to max out, I don't think I've seen anything more than about 300 megabits per second. And our latency range is in the 1 to 40 milliseconds depending on how that cell phone network is performing. And same thing on the loss. So these are all, you'll notice these numbers are all great numbers for all the applications we talked about before. They're all right in line with what we might need. On the satellite, again, depending on the satellite network that we're on, anywhere from 100 kilobits per second or 0.1 MBS, and you'll notice the B is small because that is bits, not bytes. Bytes would be a capital B. There are 8 bits per byte. Just so you might sometimes, in case you've ever wondered, why is there a small b or a little b? Well, a bit is, we take 8 bits to make up a byte. So, and when we're talking about throughput and speed, we're talking about bits, we're not talking about bytes. Bytes is how we talk about files, bits is how we talk about throughput. So 0.1 megabits per second to about 300, and latency between, actually this is down to about 25 now, and about 1,000 milliseconds. And then wireless ISPs, if you've ever stayed like at a KOA campground, or even here, you'll see a wireless SSID called OX Attendee. That's a wireless internet service provider over Wi-Fi. And so like on this little travel router I use, and I bring this with me when I travel for work, and this stays in my overlanding rig as well, I can connect to a Wi-Fi network and bring that in as a connection. I can connect my Starlink in as an Ethernet jack on the bottom, and then I can have my cell phones connect into it as well. So I can bring all of these in, and we'll talk about that as well. Out of all of these, the shortest distance is going to be on our Wi-Fi, and this is the most susceptible to that line of sight. So like camping out here in the instructor campground, I actually have this in a little waterproof bag sitting on top of my rooftop tent because it gets the best line of sight back here to the facility to connect to that OX Attendee wireless network. And one of the things that's impacting our line of sight is the curvature of the Earth. So contrary to popular belief and some internet conspiracy theories, the Earth is a sphere, and we know this because we have satellites in orbit. We know this for a lot of different reasons, but it also impacts us on the ground. And so if I were to hold my cell phone or a two-way radio at 6 feet, that signal would impact the Earth at about 3.5 miles, right? And so this is why that height, we like to say, with line of sight, height equals might. So the higher I can get my antenna up, which is why when you're walking around the expo today, you'll see a bunch of people that have WeBoost antennas, and they have their WeBoost antenna on top, and it's got a nice long fiberglass pole, and you'll see that thing that looks like a little soup can that's sitting up there. The higher we can get that up, the better chance we're going to overcome any terrain or any foliage obstructions that might be, or even the curvature of the Earth. There are some places where I camp where I might be 10 miles from the nearest cell phone tower, but I can still get a good signal because I'm making sure that I'm getting that height advantage in order to get out to that tower. All right, so this is like the ultimate basic, very basic overview of cell phone networks.
You're saying line of sight, like how do obstacles affect that, like trees?
Yeah, they absolutely do. So if you can think of RF emissions like light. So if you were to turn on a 1,000-watt light bulb at your campsite and you go 5 miles away, how well would you be able to see it? And it would be based upon, and that observation point on the other end, are there trees in the way? Are there mountains in the way? And you might even still be able to see, you could have a mountain in the way, but if the light bulb was bright enough, you might be able to see some of that glow. Some of those photons are still going to make it there, but it's going to be severely degraded. It's not going to be as bright. But if you were to get that light now 100 feet up in the air, you'd be able to see it from everywhere, right? Same concept applies here. Did I have another question? Okay. So on cell phone networks, there's only 3 nationwide carriers in the United States anymore. So T-Mobile and Sprint merged. Then we have AT&T and we have Verizon. There isn't one that's better than the other. There isn't. When we're looking at a national scale, some do better in a given market than another, but broadly speaking, their coverage is complementary typically. So I carry AT&T and T-Mobile with me, and there are tons of places where AT&T works, but T-Mobile doesn't, or T-Mobile works and AT&T doesn't. Think of them more as complementary. There are also a ton of, like, if anybody's heard of like Mint Mobile or one of those. Those are called, or Boost Mobile. Those are called mobile virtual network operators. They buy bandwidth in bulk from Verizon or from T-Mobile, and then they resell that. And so they're not the tower owner, but they operate on those same towers. And the helicopter's raising my noise floor even more.
But he's got the antenna that they're trying to reach out to, so he's up there with
Yes.
the antenna off of him.
Yeah, and your range when you're up in an aircraft is phenomenal, by the way. So, and what you'll see in here is in our urban areas, they have much smaller what are called cells on the cell phone towers. They're a much higher density population equals a much higher density of cell phone towers. And as we get out to the more rural areas, the inverse applies, right? We have fewer. And they will use lower frequencies. So like for out here, T-Mobile likes to use 600 megahertz of spectrum that they own, which propagates a lot better. It goes further than like a 1900 megahertz signal. None of this you really need to worry about. It's just interesting for you to know if you're interested in the theory of this. And what typically happens though at a festival like this, or maybe you've been to a music festival that's out in a rural area, and before everybody arrived, you had great cell phone service, and now everybody's, and you have terrible, but you still have 4 or 5 bars. And that's because we don't have the density we need of the towers, and that tower is just trying to serve too many people at the same time. And there's really not a whole lot you can do about that, except for figure out how to be louder than your neighbor. And we're gonna talk about that.
Is that like having sockets and they can only receive one signal, and then when they send it out, then they open up, and then they can get another signal and send it out?
That's correct.
You're cycling through all the people
Yep.
with a fairly...
Yeah, so we use something called time division multiplexing on cellular, and so you can think of it as time slotting. And I have a certain number of time slots I can allow somebody to talk on, and so if I have 10 time slots but 100 people, then people have to wait in order to use one of those time slots. And in the denser environments, we have more bandwidth, we have more time slots that are available, more towers that can handle that people can be redirected to. What's also interesting is that most of our modern smartphones max out at about a watt, 1.5 watts of RF power, but they're typically doing less than half a watt of RF power on that. Now, for perspective, this Midland two-way radio does 5 watts of transmit power, right? So 0.5 watts versus 5 watts. And one of the things that we're going to talk about is, well, how do I increase the power from my cell phone? And we're going to cover that here in a second. Did I see a hand? Yes.
So one of your earlier comments on this chart was that there's nothing you as a consumer or user can do about that. I'm just curious here, like only a year or 2 or 3 ago, you came here, it was impossible to get anything. It seemed like there was no bandwidth.
That's correct.
They had signal, but no bandwidth.
Right.
What did they do? They must have done something.
Yeah, so what I am aware of from only observations, I haven't actually read up on any of their FCC filings, but just from observations from being here this year, I have noticed that my T-Mobile signal is way better, and that I'm connecting on a ultra-wideband T-Mobile signal, and that wasn't available last year. So at least on the T-Mobile side,
The infrastructure's been upgraded.
that is what I have observed, but I haven't looked at any of their FCC filings, but that's my best guess based upon my observations. If you didn't know already, I love using Gaia GPS. It's my go-to for doing all of my route planning for overlanding and hiking. They actually have a cell phone coverage map if you have a premium subscription, and you can either do it by carrier or by all carriers. So you can at least get an idea of what the expected cell phone coverage is at a given spot along the route that you're following. I can't hear you.
At the last class,
Yep.
cellmapper.net.
What's it called?
Cellmapper.net. Previous instructor told us about it.
Yeah, and there's also, and then the FCC has a publicly accessible database as well. I like it on Gaia because I load my route into Gaia, and then I'm looking at the same map, just a different layer that shows what's the cell phone coverage.
Gaia can be offline once you start traveling.
Yep.
Versus the other ones, you're trying to connect to a website that you can't access.
Right, exactly. Great points. All right, so we talked about, well, there's really not necessarily anything that we can do to compete with the others, but there actually is. And this is where cell phone boosters come in. So what a cell phone booster is, it is it's effectively an RF amplifier for cell phone signals. And so what it does is we have this concept of an outside antenna, which are the ones that you'll see on all the different show vehicles, and they come in lots of different flavors. I've got one on my truck that's actually a little tiny magnet mount that's about this tall, and then I also have a directional antenna that I put up on a pole. And then we've got the amplifier itself, and then the indoor antenna. And the biggest mistake I see in people who use a WeBoost or a SureCell or High Boost or Cell-Fi, they don't put their cell phone close enough to that inside antenna. If you cannot touch your cell phone and the antenna at the same time, your cell phone is too far away from that inside antenna. I keep mine no more than 2 feet away from that inside antenna. And it's also really important that we have vertical separation between these antennas, because the way that the antenna signal radiates from these, they can interfere with each other if they're not vertically separated. You had a question?
Yeah, so in your picture, I see the cable is cinched up by the inside antenna.
Yep.
Is there a problem? Is there an advantage to having it open with the cables out?
Yeah, yes, there are two. So when we coil a coax cable, we make an RF choke. And when we make an RF choke basically reduces the overall signal available in that. It's really not a problem in my experience with cell phone boosters, because we're not trying to pull in this really faint signal. We're talking to something that we typically would have line of sight for. So really important to know, the best rule of thumb with these, they're not going to give you cell phone signal where you don't have it. What they're going to do is they're going to take 1 bar and turn it into 4 or 5, okay? So if I don't see a cell phone signal on my cell phone and I turn my WeBoost on, it's not magically going to be able to create a new cell, but it is going to amplify a signal that's already there. And one little tip is, because of the way that these work, let's say you had a 1 bar on your cell phone that you see, and you turn your WeBoost on, and you've got your cell phone right next to the antenna, and you still see 1 bar. Put your phone in airplane mode for about 30 seconds. Take it out of airplane mode. And what that does is it's forcing the radio to rescan, and it's now going to see the signal coming out of here versus trying to connect directly to the tower. And it's going to allow you to pick up that signal now. With these, height is might, right? The higher we can get this, the better. This is going to make our signal louder than our neighbors. We're at a festival or whatever. More likely that we're going to have, it's not going to create any more time slots, but we're going to be heard over our neighbors, and we're shouting where everybody else is whispering.
Are you going to get any interference from any other antenna you might have on your vehicle?
Yes, that is a fantastic point. So the question was about interference from other antennas. I have noticed RF interference on various equipment. Like I have a modified Starlink that's a flat mount that I put on top of my Tacoma, and my cell phone booster antenna is in pretty close proximity to it. And I definitely notice a difference when I turn my Starlink on and off on the quality of signal that I'm getting from that cell phone provider. Okay. And now the best thing that we can do for cell phone signals, or for all the line of sight, is because of the way that the antenna is polarized, meaning that if this is my antenna up and down, the antenna comes out in these long lobes to the sides. So what I want to do is I want to vertically separate my antennas to get the best reduction of interference between them. So I have an antenna on my hood, which isn't the best line of sight, but that's what I use for my GMRS antenna. And then my cell phone booster antenna is way above my roof. So I have fantastic vertical separation between those two, which is the best way. And if you look at any antenna tower, a professional commercial radio equipment tower, you'll notice that they have all these antennas at different points vertically on the tower, and that's the primary reason for that. Because we want to keep that noise floor low so that we have that big difference between the signal and the noise. All right, so on cellular, another option instead of using a booster is you can actually get a router with a built-in cellular modem in it. So a couple examples here that are pretty popular in the overlanding community. Peplink, they're actually a competitor of the company I work for, but they make a fantastic product. And we're going to talk some more about. They make a really good product, and they've got a really neat way that they can combine signals that we're going to talk about. We've got the MoFi or the MoFi and InstiConnect. And InstiConnect is here. They're in the indoor area. So if you didn't know, there's like a warehouse over here, indoor area, and they actually have flush toilets and a sink you can wash your hands in. InstiConnect is here. And what they do a little differently is they put the cellular modem inside this enclosure. So we eliminate any of the loss that happens with that cable, which is brilliant. I wish more of these companies would do that. Where on the other ones, I'm typically running multiple coax lines up, and then there's loss that's experienced in that. But they all do the same thing. They just have different features that they offer in that.
Are they all equally effective?
So if you are looking to have the best possible cellular connection, the longest range, hands down InstaConnect is the best. That is what they do better than anybody else. If you're looking for the Swiss Army knife that will do everything, and you can pull in your Starlink and you can aggregate it and you can have multiple different carriers and eSIM cards, Peplink is my recommendation there. And then Mofi's kind of that middle ground in between. It's got some of those features of one, but not the other.
Excuse me. I have a question here.
Yes?
For the InstaConnect, does it require cellular service?
Yes. Yeah, so with all the ones I just talked about, you are effectively bringing in a SIM card dedicated to that device. There's another way that I do it that I'm going to talk about in a little bit, which is the less expensive way, and I've had fantastic results with it. And I actually don't use a Peplink now because of this new way that I'm going to talk about here in a minute.
You're going backwards.
Yeah, I got it now. Oh, no, I'm still going backwards.
Still going backwards.
Yeah.
Better.
Okay, so satellite networks. How are we doing on time? All right, we got 20 minutes. We're definitely doing pretty well. So low Earth orbit satellites. Why do low Earth orbit satellites matter? They matter because that's how we get our low latency. So these are just, I think they're about 500 kilometers, about 300 miles above the Earth. And so for laws of physics, the time it takes light to travel, RF energy to travel from that, is how we're able to get to this low latency on that. There is really only one usable, accessible to the average person today, and that is Starlink. OneWeb is in operation, but OneWeb doesn't deal with consumers. They primarily are dealing with commercial entities, public safety organizations, et cetera. So it is technically possible to get a OneWeb satellite connection, but I'll tell you, I work for an organization, I professionally do disaster response. In my organization, we still don't have OneWeb capability. We're working on getting it right now. We've got Kuiper out of Amazon. They have 3 satellites in orbit right now. You need about 1,000 in order to be able to do coverage. They're working on it. It is coming from Amazon, so I'm going to be really excited when it comes up because Amazon does data centers and they do low latency networking. Phenomenal. They're an industry leader in that area, and so when Amazon's able to say that satellite downlink is going to come right into an AWS data center, it is going to be awesome, but it's not here yet. So it's just in testing right now. And then Link is the last one. They also have 3 satellites in orbit right now. They're trying to do direct cellular to satellite. They're one of the companies that are working on that. Actually, this week, Starlink just launched, in their latest launch, 3 of their satellites that Starlink launched this week have the prototype for doing direct T-Mobile cell phone to the satellite, but that's only for texting. It's not really for data. One quick note on here on the frequencies. There's a whole lot to see on this chart. The big takeaway is when we're talking to something in the sky, weather can interfere with our signal. And specifically on Starlink, they're on the downlink to the data center. So our signal goes back and forth to the satellite, and the satellite relays that to one of their data centers. And that downlink on the data center is susceptible to water absorption. And so I've had great success using Starlink even in a thunderstorm, but you get a massive hailstorm or you get a snowstorm, and you can end up with significant dropouts on that. Also, the ionosphere. We had some pretty massive solar flares in the past 2 weeks with some coronal mass ejections. We were able to see northern lights even at this latitude. That also caused interference with Starlink. So these are just things to consider. And there's really nothing we can do about it. I'm going to go through these slides, this animation pretty quick, because the main point of this I know I have all the frequencies in here, but the big thing is on Starlink, we've got a bunch of different antennas, and I'm going to show them here in a minute. We need great line of sight. I say, put your arms out wide, look up to the sky, from the ground to straight up, and then 180 degrees either side. That's the ideal view of the sky I should have for using Starlink. It will work if I have less than that, but I'm going to have some drops, which is going to result in loss, and then we've seen what happens when we have loss in there, right? Now, the way that it works, who here has Starlink today? All right, so the older Starlinks, they're not selling these models anymore. They have a mast on them, and they would articulate. And so you would turn it on, and it would kind of turn flat. It would get its bearing, and then it would point to the nearest pole. So in the northern hemisphere, it would kind of tilt towards the northern hemisphere, and then the southern hemisphere, the opposite. And the reason for that is because of actually where the geostationary satellites are, so we don't interfere with them. But what you'll notice is that those satellites are moving across the sky pretty quickly. They're only visible for about 3 or 4 minutes as they're moving fast because they're so low in order to stay in orbit. And you'll notice that on that articulated mount, it's not moving. You'll say, like, why isn't this tracking? Like, I've got this nice window in the trees here. I don't have 100 degrees. I've got like a 10-degree window, but I can see right where the satellite's pointing. Well, that's because it uses what's called a phased array antenna. These are the coolest thing ever. Like, I love this concept of phased array antennas. What it does, there are hundreds or thousands of antenna elements in here. And if we've ever thrown a pebble into a pond, we see the ripple that goes out. This does the same thing, but it'll time which antenna sends the signal in order to cause interference patterns in those ripples to create a directed signal. So it's doing this hundreds of times a second, where it might send the signal out of this antenna and then that one and then that one in order to create a virtual directional antenna, beamed formed antenna. It's so cool. I love the physics that's involved in this stuff. Modern Wi-Fi will do that as well. So Wi-Fi 5, so 802.11ac and Wi-Fi 6, they have that same concept with what's called multi-user MIMO, where they can do dynamic beam forming. But that's why you don't see this antenna moving and tracking, is because it's doing it virtually. So it really does have this 180-degree view of the sky, and then it's actually 100 degrees vertically that it can see as well. All right, we talked about kind of the impact of doing of latency, and this is actually from the Starlink website. They show, hey, if you've got like a HughesNet, DirecTV, a Viasat satellite out here as a geostationary satellite, which is roughly the same distance as the circumference of the Earth, and that's just kind of how orbital physics works. In the same amount of time it takes to send one message back and forth on Starlink, the same amount of time it takes one to send to the geostationary, we can send 70 on Starlink. And that's why that latency and that performance is so much faster. Has anyone here ever used a Viasat or HughesNet or a geostationary satellite? And how did the performance feel on it? It felt slow. You might have had 100 megabits of throughput. Like if you had started a file download, it might hit 100. But the problem is that's not how we normally do. We're usually on the web and clicking things and scrolling, and we want that. We need that very fast conversation, just like when I was talking to Roland and we had that long delay. It felt really awkward and difficult. There was a hand that raised. Yes?
I was wondering, what you just said after multi-user MIMO.
Yeah.
What was the second thing you mentioned?
Yeah, so multi-user MIMO is on Wi-Fi, does that same concept of dynamic beam forming. So the same thing that we're doing in a phased array. And what's different between a phased array is a phased array is effectively a panel antenna. It's built like this with the antennas at very specific distances. On the multi-user MIMO, that still can apply to this technology, but it's not this panel antenna. So on a router, like on this guy, this is a Wi-Fi 6 capable. It's got 2 Wi-Fi antennas on here. It actually can do dynamic beam forming with those 2 antennas, but it's nothing compared to what we're doing on these, right? All right, so these are all of the Starlink dishes that have been available over time. These have been, this column here has been completely phased out at this point. You can still get a high performance articulated, but the 2 main ones right now are both flat mounts. We've got the high performance flat mount and then the standard flat mount. So they've got Both of these are the type of that we would mount either on a cabin or on a boat or on an RV or in an overlanding truck. The primary difference between these is going to be the performance and the cost. And there's a massive cost difference between the two. The standard dish is about $600 brand new. The high performance is about $2,500 brand new. They work on the same plans. As I understand it, the Rev4 standard doesn't technically support in-motion use today over 10 miles an hour, but I also understand it does work. So, yes?
Is there a secondary market for the high performance?
So Starlink does sell refurbished.
Okay.
And you can find them, but be careful when you're buying a used Starlink because the service is tied to the antenna itself. And you have no way to pull off. It's almost like if you were to buy an Apple product, you have to make sure that the previous user removed themselves from it, or you won't be able to activate it. It'll become a paperweight.
Okay.
Now, unless you're really needing to use it in motion above 10 miles an hour, which you may have that use case for it, the Rev4, the current standard is fantastic. You're going to get 200 to 300 megabits download speed and about 30 megabits upload speed on that. This is really if you're needing that in-motion data above 10 miles an hour. Yes?
Have you heard in your crystal ball, have you seen what the next level of technology for Starlink is? I heard they're going to even have a smaller...
That's correct. So Starlink has received FCC approval for a portable dish. The FCC filing said it was going to be, I think it was something like 12 by 12 inches, that range. And I have not encountered performance problems with Starlink. My biggest Starlink consideration is power consumption. So my Starlink, I have the Rev3, also called a Gen 2, very confusingly. But I have a Gen 2 articulated Starlink that I cut the mast off, 3D printed an enclosure for it, sits on top of my Tacoma, and I converted it to 12 volt. So I average about 40 watts of power consumption, where if I had plugged that into an AC inverter with their equipment, I would be averaging closer to 75 to 90 watts of power consumption. And you're like, oh, well, that's not that big of a difference, but I'm running on a 100 amp hour battery, and you're typically running that for many hours at a time. And so having half the power draw on that matters to me, and so I did the work to do that conversion. On the high performance ones, we're typically, I professionally deploy the articulated and the flat high performance. They are typically sitting around 100 watts doing normal traffic, but will peak up to about 300 watts of power consumption.
Per hour?
300 watts. So over an hour, that would be 300 watts out, 300 watt hours that have been consumed. Yes? Nope, doesn't affect it at all. So I use a kit called Boondocker, boondocker.io. They're out of Australia. I love their kit. I don't have experience with any of the others. That's the kit I use, and I use that one because my favorite overlander, Jason from Overlanders, he did a video on YouTube about it, and he is my idol. Like, I love Jason. He's fantastic. He's always making microcontrollers out in Bolivia and doing cool stuff. So when Jason recommended it, I'm like, all right, I'm buying it, and it's been fantastic. And that's what I use in my Tacoma out here in the instructor area. The question about total power consumption, it's going to vary. So it sits at about 100 watts on this guy, but could go up to 300. So if I'm measuring that over the course of an hour, maybe I'm 150 watt hours consumed within a given period of time. Yes?
So, I hear Gen 3 terminology. Which of those devices? Is that the whole?
Yeah, no. So it's very confusing because they have the Rev and then the Gen. And so if I move on to my next slide, hopefully, so really these are your two options that you have. You have the standard, also known as the Roam, which is the $600 device, and then that is what the community is calling the Gen 3 residential Starlink. And then you have your high performance one. And this is all on the Starlink website, and they've got the different use cases on here. I pay $150 a month to be able to take this wherever I want. I use it as my backup connection at home. And so I have a terrestrial connection at home, and then I use this with my backup. I'm going to move on because we've got to talk through some advanced stuff. This is my evolution of my setup. When I first got it, I used a Christmas tree stand to put it out in a field and ran a long cable. And then this is up at the north rim of the Grand Canyon. This is my truck before I added my solar panels. You can see I've got it up on a painter's pole, and so it's sitting about 24 feet up in the air. And then I had even tried mounting it on my roof rack. Now this is where it sits on my truck most of the time. Now I did still make it so that I designed and 3D printed a part to go underneath that allows me to still put it on the end of this pole. And why would I put it on the end of the pole? Anybody? Line of sight to have that better view of the sky, right? And then this was, this isn't loading. This was an example from last year. And of course my slide didn't load, but it was just showing that even with this view of the sky, I was getting dropouts about every two minutes because of that. Yes? Of course, yeah, because it's about capacity. It's about, so if I'm out on BLM land out north of the Grand Canyon, you know, south of St. George, I get 200 megabits per second, 30 megabits of download. At my house in Phoenix, you know, I'm 70 megabits typically, maybe 10 megabits upload. And then I don't think I have a screenshot in here for it, but I was doing some overlanding in southern Arizona recently. Oh, I do have it in here. I just had it as an animation. Yeah, there's all my dropouts that you can see from that view. All right, so this is the most important part of the talk. If you don't take anything else from this talk, this is the most important. Without the technology I'm going to talk about, you can't just say, oh, I want to combine my Verizon, my AT&T, and my Starlink all in one and have a great performance. It just doesn't work like that. We have to use what's called a bonded VPN, which requires a cloud service and then either special hardware or software on your side in order to combine all of these so we get higher bandwidth, higher throughput, lower latency, lower loss. And so yes, this can be done with the right equipment. I'm going to breeze through these because we're getting close on our time. Failover is just if one link fails, I automatically switch to the other. Load balancing is if I am sharing across multiple links per user or per session. It does, so if I have load balancing enabled, and you'll see some of these routers have load balancing, it just means it's going to send you know, John's traffic on Starlink and Lyle's traffic on AT&T. That's load balancing. What's really important is link bonding. Link bonding is the most important thing of all of this, and that's where I'm able to take these connections and make them look like one really fat pipe, one really big internet connection spread across all of those. And then ideally, I'm going to layer on top in software or hardware forward error correction on that. And so even if my application, so maybe I need to use Microsoft Teams, which doesn't have forward error correction, but and I can't use WebEx, which does, I can still run it through a link that does forward error correction on the link. So if I'm not doing the application layer, I can at least do it on my connection layer. And so there's really two ways to do that today. One is with Peplink, and they have a cloud service called SpeedFusion. They do a phenomenal job. They're my competitor. They do a fantastic job. I love their products. They work really well. You have the ability to aggregate any number of connections you want. You're typically, though, going to have to bring in your own dedicated cellular SIM card for each one of those connections you want, then obviously bring in Starlink via the Ethernet interface. And they do that via a service called SpeedFusion. So that will work just by as long. You can buy the product and you've got all these connections available to you, but the real power is when you subscribe to SpeedFusion, which is where they're now sending that traffic across all links. And as a paid subscription, you'll see in here, they'll charge you $40 to have 1 terabyte of traffic pass through their servers. So not bad. It's really not a bad price at all. And it maxes out at 200 megabits per second of throughput. But what's cool is their software in their router, if you really want to get into the configuration, you can say, don't send Netflix to SpeedFusion because Netflix doesn't care about latency and loss, but heck yeah, send my Microsoft Teams and my Zoom traffic through SpeedFusion because that's where it really matters. And you have really great granular control over which link you want to send traffic on and which link and whether or not you want to use SpeedFusion when you send that traffic. Because again, I don't care if it takes 2 minutes for an email to send, but I really care if I lose 2 minutes of a video conference, right? Now, that's the That's the high-end way to do it. The poor man's way to do it, this is the way I do it in my vehicle. So I use a service called Speedify. Anybody can do this. You don't need any special tools. All you need to have is the Speedify service. They charge $100 for 2 years of service. You install the app on your smartphone, on all your smartphones. You can have it up on 5 devices on your laptop. And then what you do is on your laptop, you connect to the same Wi-Fi network. So in my truck, I've got it here. I bring my Starlink into this. I connect my AT&T cell phone onto that same Wi-Fi network. I connect my T-Mobile cell phone onto that same Wi-Fi network. I connect my laptop onto that same Wi-Fi network. I turn Speedify on the app on all those devices, and now all the devices see every other device's connection, and it's bonded. So now my iPhone here sees AT&T, T-Mobile, and Starlink. My laptop sees AT&T, T-Mobile, and Starlink, and it's telling it all through all of these at the same time. You can do this even at like a hotel. You connect to the hotel Wi-Fi. Depending on the hotel, they may or may not allow devices to talk to each other, but that's where my travel router comes in, because I'll bring my travel router in, I'll tell my travel router to connect to the hotel Wi-Fi, and then I connect all my devices to my travel Wi-Fi. And now my laptop, my tablet, my phone, they all see the hotel's network, and they see my AT&T signal and my T-Mobile signal. And I could bring in a Verizon iPad in there too if I wanted and have all 3 carriers. But the great thing is it's now going to connect and use all of those at the same time. The downside is it maxes out at about 200 megabits per second. In my experience, they don't have an official max, but that's been my experience using it for over a year now. That it tends to max out there. But this cool thing is anybody can do this. You don't have to have a special router. You don't have to know how to configure a router. But if you do, this router, you can actually put a custom firmware on it that has it built inside. So I actually run this with a custom firmware. If you're a tinkerer like me, you're not afraid, you can do, but it's not necessary. It's not required.
What's the name of that particular router?
So this is the GL iNet Slate AX. But any of the GL iNet line, if you don't care about tinkering with the firmware, they make great travel routers, and they've got an app on your phone, and you open up the app and you say, oh, I want to connect to the hotel Wi-Fi. You don't have to know how to configure a router. You're just following the app that comes from GL iNet.
Cool.
I had a couple screenshots in there. I think we're right at time here. So in summary, latency and loss have a huge impact on throughput. The way we overcome that is through bonded VPN. The 2 ways that I know of that you can do that as a regular user and not a big company is either by using the Peplink SpeedFusion service or by using Speedify. I have yet to find any others out there that a regular person can go and buy. Lots of stuff if you're a big company and you're a network engineer, but for a regular consumer, those are the only 2 that I know of. We want to get our cellular connections up as high as possible. Like even when I'm camped here, in my rooftop tent, I've got pockets in there that I keep my cell phone in on the charger and connect into this because it gets me up higher and gets me a better signal on there. Line of sight on the sky for Starlink matters a lot, even though it doesn't seem like that Starlink antenna is pointing, it's going to be able to see all this, but because of that phased array antenna, it can see quite a long way, and we already talked about the benefits of bonding those connections. All right, so I have another class. I've got to start in 8 minutes in another room. I'll take 2 minutes of questions, and then I'm going to be around all weekend. I'd love to talk to whoever.
Clouds.
Yes.
Starlink. Good or bad?
Yeah, so generally speaking, regular cloud's not a problem. You get a hailstorm, you're going to get dropouts. There's another question.
I noticed you're recording. Can we get a link to the
Maybe, and I say maybe because I haven't seen what the footage looks like yet, whether I had any audio dropouts, whether or not I even got my face in any of it. So ideally, I would post this on my Tech with Lyle YouTube channel, which has like 30 followers today or something silly like that, but that's the intent. Yes?
Have you experienced with certain boosters working better than others?
It is less about the booster manufacturer and more about whether or not it's FCC certified. That's number 1. And then number 2, it's about how you do your antennas.
Okay.
Yeah. And number 3 is the bands that it covers. Not all cell phone boosters cover all cellular bands. So it's important if maybe you have T-Mobile and you care about band 66 or band 12. You need to make sure that that's available on that booster. Yep.